In this video, we will be covering integration by substitution. We're going to split this discussion up into two separate parts, one of which we will be discussing pattern recognition, and the second of which we will be looking at a change of variables. Both of these techniques involve something that in calculus we call a U substitution. So the whole idea behind substitution is really based on the chain rule. So a few lessons ago, we learned that if we're trying to take the derivative of a composite function, so again, looking at this notation, we can see that we have a smaller function g that has been plugged inside of a larger function f. Chain rule tells us we take the derivative of the larger function f, keep the inside the same, but then multiply by the derivative of the inside. So now we're going to use that inverse relationship between derivatives and integrals to conclude basically that if we integrate both sides of this, so you'll notice now we have the integral of that on the left side, that we should cancel out this derivative and be left with capital F of g of x. And of course we add on our constant of integration. And that is exactly what theorem 4.13 tells us. It tells us how to take the antiderivative of a composite function. Oftentimes we will see that this g of x will be replaced by the variable u. That is us using a change of variables. And so this here is the alternate version of theorem 4.13. Same thing, just written in a different notation. So when we go through these U substitution problems, what's going to be key for us is that we're making a choice of U so that we see the derivative or a constant multiple, and we will see several examples of that showing up in that integral. So when we're doing substitution to integrate, it's essential that we know our derivative rules well, because that will help us recognize the pattern that we're looking for. So let's look at our first example. Example 1a. We want to find the antiderivative of this expression in here. So thinking back to that discussion on pattern recognition, I can see that I have an inside function, x squared plus 1, right? Because that's on the inside of this square function. And then conveniently out here, we have a 2x, which happens to be the derivative of what we have on the inside there. So first, I'm just going to start off and rewrite this integral using that U substitution. I'm going to intentionally choose to let U be what we have on the inside of those parentheses, x squared plus 1. Now I'm going to take the derivative of that U, which I will write as du. The derivative of x squared plus 1 is 2x. And because we're going through integration, we're going to include a dx on the end of that. So now I can rewrite this integral using the things that we have set up in this substitution. So now instead of writing x squared plus 1 squared, we let x squared plus 1 be u. So we have u squared. And then for this 2x dx was our du. So we now have rewritten the integral in a much simpler way to have u squared du. We'll use the power rule for integration, increase our exponent by 1, divide by the new exponent, and remember to add on our constant of integration. Now, to get our final answer, we're going to substitute back in and replace the u. So we had let u equal x squared plus 1. So there's our u. We cube it. It was divided by 3, and the constant of integration c was added onto it. And there is our final answer. So again, when we started this problem, the reason that I chose u to be x squared plus 1 is because the derivative of x squared plus 1 showed up in the integral. So you have to choose your u value so that when you take the derivative of u, you're left with something that is in the integral. Let's look at example B. Again, we can see we have a composite function, something plugged in on the inside, this x cubed plus 1. If I think about what the derivative of x cubed plus 1 is, it is 3x squared. So x cubed plus 1 would be a very good choice for u. I'm now going to take the derivative of u, which we call du. It is 3x squared, and remember to keep a dx on the end of that since we are dealing with integration. So now I can rewrite this integral just to help us wrap our heads around this. I'm first just going to move some things around so you can see what's happening. I'm going to move the square root to the front, and then this 3x squared I'm going to move to the back. So this is now just going to be a 3x squared in the back with the dx. That step's not necessary, but I think first time looking at substitution, it's helpful to see. So now let's start rewriting this. Well, we had let this x cubed plus 1 be our u. So now instead of the square root of x cubed plus 1, we have the square root of u, which when we're integrating is more convenient to write as u to the 1/2. So this u to the 1/2 takes care of all of that. That's all been substituted in for. Now let's deal with this 3x squared dx. Well, 3x squared dx is du. So now we have a much simpler integral that we can integrate. Using the power rule for integration, we're going to increase our exponent by 1. 1/2 plus 1 is 3/2. And then we need to divide by our new exponent and add our constant of integration. I'm going to clean this up a little bit because dividing by 3/2 is the same thing as multiplying by 2/3. And then finally, we're going to substitute back in so that we're not leaving our answer in terms of u. I'm going to replace the u with the x cubed plus 1 that it is equal to give us our final answer. Let's move on and look at example C. I'm missing a set of parentheses right there to finish off that integral. So again, I want to make a choice of u so that the derivative of u shows up on the inside of the integral. So if we know our derivative rules, we know that the derivative of tangent is secant squared. But notice that we have this tan x plus 3. The 3 is not going to mess up the derivative of tangent being secant squared, because we do know that the derivative of 3 is simply 0. So there's our u. Let's take du. Derivative of tangent is secant squared x. The derivative of 3 is 0, so I don't need to put anything there, and I have a dx on the end. If it's helpful, I will rewrite the order of the factors inside of this integral. So all I did was just move this secant squared x to be at the back with that dx. And now we can clearly see that this tan x plus 3 is our u, and that this secant squared x dx is our du. So now we're just integrating u du. We integrate by increasing the exponent by 1 and dividing by the new exponent. Don't forget to add your constant of integration. And then finally, I will substitute back in for u, which is tan x plus 3. So we have tan x plus 3 quantity squared, all divided by 2, and we add on our constant of integration at the end. So earlier when we had our discussion on how to make a good choice for u, we said we wanted to choose u so that the derivative of u showed up in our integral. And in examples A, B, and C, that always happened. But there was a comment up here so that we want to choose u so that the derivative of u or a multiple of it shows up in the integral. And that's what we're going to be looking at in the next 3 examples. So following the same type of pattern, in example D, I would choose u to be x squared plus 1. Now when I choose u to be x squared plus 1, du is still 2x with the dx on the end. But the problem is I see the x with the dx on the end, but I don't have this 2, right? So I can't just substitute in for x dx at this point. So I'm going to manipulate this equation so that I only have the x dx, which means I would need to come in and divide both sides by 2 and get that 1/2 du is equal to x dx. So I'm going to briefly rewrite this integral. This step is optional, but again, I think first time seeing u substitution, it is helpful. So all I did was take this x and move it to the back of the integral so that it's next to the dx. Now let's actually start substituting. I'm going to replace this x squared plus 1 with u. So I now have u to the fourth. And then for the x dx, we're going to replace that with a 1/2 du. Now the 1/2 is a constant, and we learned earlier that we can pull constants out in front of the integral and simply be left with this u to the fourth du. Now this is something that we can integrate easily using the power rule for integration. We increase our exponent by 1 and divide by our new exponent. Make sure to add on our constant of integration. I'm going to clean this up a little bit. This is 1/10 multiplying the 2 and the 5, u to the 5th plus c. And our final step would be to substitute back in for u, which is x squared plus 1. Still raised to the 5th power, still with our constant of integration added on at the end. So when we make a choice of u and what we get as our du is off by a constant, some multiple of it, we're able to manipulate that equation to solve for exactly what we have left in the integral and then proceed. Let's look at another example. Example E is very similar to example B. We're still going to choose u to be x to the 3rd plus 1. And the reason that we do that is because when we take du, we get 3x squared dx. I do see the x squared dx in the integral, but I do not see the 3. So I want to get rid of that 3. I'm going to divide both sides of this equation by 3, giving me 1/3 du is equal to x squared dx. And now I'm able to start my integration. Same as last time, I'm first just going to rewrite this integral so that it looks more convenient to us. If you want to go ahead and change the square root to the 1/2 power, we can also go ahead and do that. Let's start substituting. I'm going to replace the x cubed plus 1 with u. It's still raised to the 1/2 power. And I'm going to replace the x squared dx with a 1/3 du. Same as last time, that constant of 1/3 can come out in front of the integral, leaving us with the integral of u to the 1/2 du, which we know how to integrate using the power rule. We increase our exponent by 1. Dividing by our new exponent, dividing by 3/2 is the same as multiplying by 2/3. And we remember to add on our constant of integration. I'm going to clean this up a little bit. 1/3 times 2/3 is 2/9. And then I will replace the u with what u was equal to, which was x cubed plus 1. We always want to make sure that we get our answer back in terms of the original variable, which was x. And there is our final answer. Now let's look at example F. Same as last time when we looked at example C, I'm going to choose u to be the factor that contains the tangent. So I'm going to let u equal tan x plus 3. Taking the derivative, du, the derivative of tangent is secant squared x. The derivative of 3 is just 0. Make sure to add the dx on the end. The problem is I do not have a secant squared x dx. I have a 2 secant squared x dx. So this time I'm going to multiply both sides of this equation by 2 so that I have an expression of which I can substitute in for this 2 secant squared x dx. I'm going to again rewrite this integral. I won't do this much longer, but again, it's helpful to see where everything goes as we get into our substitution. So I will be replacing the tan x plus 3 with u, and I will be replacing the 2 secant squared x dx with a 2 du. The 2 is a constant that can come out in front of the integral, leaving us with the integral of u du. which we integrate by increasing our exponent by 1 and dividing by our new exponent, remembering to add our constant of integration. We can simplify this because the 2's cancel, leaving us with simply u squared plus c. And as our final step, we will substitute back in what u was, which was tan x plus 3. It's still squared, and we still have our constant of integration added onto it. Example 2 is going to be very similar to example D from example 1. When I look at this expression, I see this x squared plus 1 on the inside of those parentheses that is being squared, and I see this x on the outside. I'm going to choose u to be x squared plus 1, because when I do that, our du is 2x, that's the derivative of x squared plus 1, and we added dx on the end. Now I do have an x with a dx on the end, but I don't have this 2. So I manipulate this equation by dividing both sides of it by 2, so that I know exactly what to substitute in for x dx. So now I'm going to briefly rearrange this integral before we start substituting in. Let's start substituting. I'm going to replace the x squared plus 1 with u. It is still squared. And then I will replace the x dx with a 1/2 du. You can go ahead and stick the 1/2 on the outside of the integral and the du at the back of the integral. Now let's integrate. We still have that constant of 1/2 out in front. The integral of u squared is u cubed over 3, and we add on our constant of integration. Simplifying by multiplying the 1/2 with the 1/3 to give us u cubed over 6. And then finally, we will substitute back in what we have for u. I replaced u with x squared plus 1. It's still divided by 6, and we still have our constant of integration. So in all of these examples, we have gone ahead and used a change of variables by introducing this new variable of u. And what that did in every case is it gave us a much simpler integral that we can integrate. I think everyone would agree that integrating this looks a lot simpler than integrating this. We're going to continue to do that by making good choices for u. Looking at this example here, there's really only one choice for u here. I'm going to choose u to be this 2x minus 1. I don't need to take the square root with it because the square root is simply just a 1/2 power. So when I let u equal 2x minus 1, the derivative of that is simply 2, and we add a dx at the end. Now there is no 2 on the inside of the integral. I do see the dx, but I don't see the 2. So I want to get rid of that 2 so I know exactly what to substitute in for just dx. So I went in and divided both sides of that equation by 2. Now let's actually start substituting. I'm going to replace the 2x minus 1 with u. It is still to the 1/2 power. And then I will replace the dx with 1/2 du. You can go ahead and stick that 1/2 on the outside and the du at the back. And now let's integrate. We still have the constant of 1/2. To integrate u to the 1/2, we increase the exponent by 1 and divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3, and add in your constant of integration. I can cancel out those 2's to be left with 1/3 u to the 3/2 plus c, and then finally I will substitute back in what the expression for u is. It is 2x minus 1. We still have it raised to the 3/2, and we add in our constant of integration c. So here we have general guidelines for making a change of variables. We want to choose a substitution u. Most often than not, it's a good idea to choose the inner part of a composite function, which is what we did in example 3, right? We chose just the inner part, just the 2x minus 1 to be our u. We calculated du, which was the derivative of what we chose for u. And then we were able to rewrite the integral in terms of u and du. Sometimes that does involve doing some algebra to manipulate your du. so that you're only left with what you had left in the integral. Then we are able to integrate, taking the antiderivative. Let's actually go through step 6 in example 3, because if we did this correctly, then when I take the derivative of what we have for our answer to check, we should get what we started with in the integral. So let's compute the derivative of 1/3 2x minus 1 to the 3/2 plus c. We're going to need to use the chain rule. The 1/3 in the front is a constant. Chain rule here tells us to bring down the power of 3/2, keep the inside the same, decrease the exponent by 1. We're doing derivatives now, not antiderivatives. 3/2 minus 1 is 1/2. Chain rule tells us we need to multiply by the derivative of the inside, which was a 2. And then the derivative of that constant c is just 0, so we don't have to worry about that. So let's clean this up a bit. These 3's can cancel. These 2's can cancel. And we're simply left with 2x minus 1 to the 1/2 power, which is the same thing as the square root of 2x minus 1, which is precisely what we started with. So you can always check the answer to your antiderivatives by taking the derivative of your answer and making sure that it is the integrand that you started with. Theorem 4.14 is the general power rule for integration, which we have been using already. Right? We're using the general power rule for integration anytime we use the power rule for integration after doing a u substitution. Let's look at another example in 4a. Here, I'm going to choose u to be the inside of this composite function, which is 3x minus 1. I'll take the derivative of that. Du is 3, and I add a dx on the end. I don't have to do any manipulation here because I do have the 3 with the dx on the end. I'll briefly rearrange this integral to make the substitution more clear, just by writing the 3 at the back with the dx. Let's start substituting. I'm going to replace the 3x minus 1 with a u. It's still raised to the 4th power. And then for 3dx, we're substituting in du. This here is the general power rule. Increase the exponent by 1, divide by the new exponent, and don't forget to add on your constant of integration. And then finally, we substitute back in and replace u with what it was equal to, which was 3x minus 1. We still raise it to the 5th power and divide by 5, and we make sure to keep our constant of integration. Example 4b, I have 2 different factors here. I want to make sure that I choose u so that the derivative of u would show up. I want to show you a non-example, a bad choice for u. So I would not do this if I were you. If you choose u to be 2x minus 1, then your du would be 2dx. And a du of 2dx does not help you substitute anything in for that other factor of x squared plus x. On the other hand, if we choose u to be x squared plus x, then when we calculate du, we would have 2x plus 1 with the dx on the end. So I make sure to wrap that 2x plus 1 in parentheses, which is perfect because I do have a 2x plus 1 with a dx on the end. I'll briefly rearrange this integral so that the substitution is clearer. And now let's start substituting. So I'm going to be replacing the x squared plus x with a u, and I'm going to replace the 2x plus 1 dx with du. We know how to integrate u du. It is u squared over 2 plus c. And then finally, we will go back in and substitute in what we have for u. Now let's look at example 4c. I'm going to make the choice of u to be what's on the inside of this composite function. U will be x cubed minus 2. And I do that because I can see that if I choose u to be something with an exponent of 3, that then when I take du, I will have something with an exponent of 2. I can see I'm missing an integral right here. Please add that in right there, that integral in front of this entire expression. So I have du is 3x squared. I'll add a dx on the end of that. I'm going to briefly rearrange this integral. I'll put the square root at the front and the 3x squared dx at the back. Let's actually start substituting after we replace the square root with the 1/2 power. It's just a little bit easier for us to look at that. So I'm replacing the x cubed minus 2 with u. It is still raised to the 1/2 power, and I'm going to replace the 3x squared dx with du. Now we can integrate, increase our exponent by 1, divide by our new exponent, and add in our constant of integration. And then finally, we will substitute back in what we had originally in terms of x for u to get our final answer. Let's look at example D. We want to make a choice for u so that the derivative of u shows up in the integral. Well, using our knowledge of derivatives, I'm going to choose u to be 1 minus 2x squared. I don't need to include that squared that's on the outside, right? Because this is just going to be the exponent that we have on u. So u is equal to 1 minus 2x squared. Taking the derivative of that, du would be a negative 4x dx, which I do conveniently have on the inside of that integral. So now let's actually start substituting in. So in the denominator, I'm going to be replacing the 1 minus 2x squared with u. It's still squared from this exponent of 2 on the bottom. And then all of this negative 4x dx, is du. So we are left with the integral of u to the negative 2 du. I'm going to increase my exponent by 1, divide by my new exponent, and add in my constant of integration. First, just going to use some algebra to rewrite this expression so that it looks a little bit neater. Because I had u to the negative 1, I can rewrite it with a positive exponent if I put it in the denominator. And this minus 1, it doesn't matter if it shows up in the front, in the bottom, or on the side of the fraction, as long as it is there. So now let's substitute back in what we had for u, which was 1 minus 2x squared. We don't really need parentheses around that anymore, and we keep our constant of integration, c. Let's look at example E. We want to make a choice for u so that the derivative of u shows up in the integral. We can see that we do have some composition in here since that cosine is squared. So I'm going to choose u to be cosine x. The derivative of cosine is negative sine x. Keep a dx on the end. We do not have the negative. Right? I don't have the negative in front of this sine x, and so I'm going to multiply both sides by negative 1 or divide both sides by negative 1, same thing, to see that negative du is equal to sine x dx. So now let's actually start substituting in. I'm going to replace the cosine with u. Remember that that cosine was squared, so u is squared. And I'm going to replace the sine x dx with a negative du. The negative is a constant multiple of negative 1, which we can put on the outside of the integral, and I can put the du at the back. So now we know how to integrate u squared. It is u cubed over 3. Make sure you keep that negative in the front and add on your constant of integration. And then finally, I will substitute back in what we had for u. U was cosine x. Remember to keep it cubed and divided by 3, and then add in our constant of integration, c. So far, all of the examples that we have looked at that involved the change of variables did not have limits on the integral. So far we've only looked at indefinite integrals. Example 5, using theorem 4.15, is going to help us evaluate now a definite integral with limits on it. Before we get into the limits, let's focus on what substitution we want to make. We've seen an example very similar to this earlier. I'm going to choose u to be the inside of that composite function of x squared plus 1. Then my du is 2x dx. I do not have a 2, so I'm going to divide both sides of this equation by 2 to see that 1/2 du is equal to x dx. And now we can actually start doing some substitution. So first, I'm just going to start with reordering the factors of the integral so that the substitution is clear. So I'm going to move the x to the back with the x dx. Now I'll start substituting. I'm not going to put any limits on the integral right now. So I'm not going to write 0 and 1 as my limits right now. I'm going to replace the x squared plus 1 with u. It is still cubed. And I'm going to replace the x dx with a 1/2 du. I'll stick the 1/2 in the front of the integral because that's a constant, and put the du at the back. So we've taken care of the substitution. Now let's talk about the limits. So the issue is that these current limits of 0 and 1 correspond to the variable of x, because right now this integral is written in terms of x. We have rewritten the integral using a change of variables in terms of u. So in order for me to put limits on there, I need to have my limits written in terms of u rather than in terms of x. So we started off with x limits of 0 and 1, and we made the substitution that u is x squared plus 1. So if x is 0, plugging that in would be 0 squared plus 1 to give us that u is 1. So now instead of a lower limit of 0, I plugged that 0 in for x and got that u is equal to 1. So when x is 0, u is 1. Let's see what 1 turns into when we write it in terms of u. So when x is equal to 1, I'm going to substitute that into this expression for u. I would have 1 squared plus 1, which is 2. So when x is 1, u is 2. So I changed my limits on the integral using what we have for the substitution. So now let's continue. We know how to integrate u cubed. It integrates into u to the 4th divided by 4. We need to evaluate this from 1 to 2 using the fundamental theorem of calculus. So I'm just going to simplify this first. I have u to the 4th over 8. It has limits of 1 to 2. Fundamental theorem of calculus tells us to plug in our upper limit first, subtract, and then plug in our lower limit. So we are left with 16 over 8 minus 1 over 8, which gives us 15 over 8 as our final answer. The last examples I have in this lesson are 2 problems that I would like for you all to try. This is missing a 2x right here. Add that in for me, please. I want to get you started on example 6a. I'm trying to integrate sine squared x dx. From trigonometry, there is a formula that tells us that sine squared x can be rewritten as 1 minus cosine 2x divided by 2. I'm going to rewrite that integrand, separate that fraction into a 1/2 minus cosine 2x over 2 dx. So I just broke this fraction up into 2 separate terms, which breaks this integral up into 2 separate integrals. The integral of 1/2 and the integral of cosine 2x divided by 2. If you wanted to, you could pull out this division by 2 in front of the integral and have it as a constant out in front, as so. Now the first integral, the 1/2 dx integral, that's very straightforward to integrate. This second integral involves a composite function because it's not just x on the inside of cosine, it is 2x on the inside of cosine. So when you go through this integral, you're going to want to use a substitution where you let u equal 2x, so then that your du is 2 dx. But we don't have that 2 on the inside of the integral, so you'll manipulate that to get a 1/2 du is equal to x dx. This is hopefully a good start to help you start integrating this expression here. In both of these examples, I give you what you should have for your final answer. Please try to complete those, and if you have any issues working through them, shoot me an email and I'll be more than happy to help.